Hi, I'm Barbara Andrews, and building a great model is only half the journey. The real challenge is getting that model to run reliably in the real world. In this section, you'll explore how to plan and prepare an MLOps solution with Azure Machine Learning, transforming experiments into scalable, production-ready systems. You'll see how practices like versioning, automation, pipelines, and monitoring bring the discipline of DevOps into machine learning. The results? The models can retrain, deploy, and improve continuously, enabling teams to deliver AI solutions that stay accurate, traceable, and ready for real-world impact. Designing an MLOps architecture for operationalizing machine learning with Azure Machine Learning has a 6-step life cycle. Step 1, setting up the infrastructure. Step 2, the inner loop where data scientists explore data and train models. Step 3, continuous integration to package and version models. Step 4, deployment to production environments. Step 5, continuous delivery in safely promoting tested models. And step 6, ongoing monitoring to track model and endpoint performance. Remember that MLOps is typically a team effort. Data engineers may manage data storage such as Azure Blob Storage. Infrastructure teams provision resources like Azure Machine Learning Workspace, and data scientists focus on model development, while ML engineers handle deployment. For example, imagine a demand forecasting model for retail. Data engineers maintain the pipeline that lands sales data in storage. Data scientists train and improve the model. That's the inner loop. And ML engineers deploy and monitor the model in production. That's the outer loop. Here's why monitoring is essential to every MLOps solution, because a model that performs well today may degrade over time as data patterns and environments change. Effective monitoring means continuously tracking performance metrics such as accuracy, precision, recall, or F1 score, and watching for gradual drops that signal potential problems. It also involves detecting data drift, changes in input feature distributions or target outcomes, and concept drift, while the underlying relationship between features and predictions change, often due to real-world shifts like market trends or evolving customer behavior. Consider how a fraud detection or customer churn model might initially perform with 90% accuracy. But if the accuracy drops below a set threshold, for instance 80%, due to new behavior patterns in incoming data, that drop should trigger retraining using fresh data. It's a good practice to treat monitoring as a continuous lifecycle activity, not a one-time check. Track metrics regularly, watch for drift, incorporate new data when available, and use scheduled retraining, for example, quarterly or monthly, to keep production models reliable and relevant. In modern ML workflows, training a model once isn't enough. You need a way to automate training so improvements happen continuously and reliably. This is where GitHub Actions and Azure Machine Learning come together. By connecting your source code repository to automated workflows, every important change, like a new data set, updated training script, or a merged pull request, can trigger model training automatically. In this section, you'll see how DevOps practices extend into machine learning with GitHub Actions orchestrating Azure ML jobs. The result is a streamlined MLOps pipeline where experimentation, versioning, and training happen seamlessly. As part of your development workflow, helping teams deliver AI updates faster with consistency and confidence. Modern MLOps starts with source control by storing training code, prompts, and configuration files in GitHub. Teams can track every change, collaborate through pull requests, and roll back quickly if something breaks. When you integrate GitHub with Azure Machine Learning, those repository updates can automatically trigger CI/CD workflows with GitHub Actions, running training or evaluation jobs in your Azure ML workspace while sensitive credentials stay protected using GitHub secrets. This benefits a team that updates a model's training script in a GitHub branch. When the pull request is merged, a GitHub Actions workflow automatically runs a training job in Azure ML to validate the change. Consider keeping all ML code and configurations version controlled and connect repository events, push or pull requests to automated Azure ML jobs. This ensures experiments are reproducible, collaborative, and production ready. Here is a sample of a production-focused GitHub workflow, often used with MLOps. The main branch here holds stable production code, while changes are developed in short-lived feature branches. When a contributor finishes work, they open a pull request to merge into main. The pull request automatically triggers GitHub Actions, which runs checks behind the scenes, such as linting and unit tests, to verify that the change is safe and maintainable before it's merged. For example, a data scientist improves a training script for a churn model in a feature branch. When the pull request is opened, GitHub Actions automatically runs the validation tests, and after passing those checks, the lead data scientist reviews and approves the merge to main. Some best practices are keep feature branches small and short-lived, rely on automated CI checks for quality control, and protect the main branch so only reviewed, test-passing code reaches production. Here is a code snippet of our GitHub's action workflow designed to run an Azure Machine Learning job. The YAML workflow is named Manually Trigger an Azure Machine Learning job, and it uses the workflow dispatch trigger, meaning the workflow can be launched manually from the GitHub interface. The job defined in the YAML training model here runs on an Ubuntu latest runner. The workflow then performs two main steps. Step 1, authenticate with Azure using the Azure login v1 GitHub action and credentials stored securely in our GitHub secrets, Azure credentials. Step 2 is to execute the Azure ML CLI command, azml job create, and then we have here file, your source, and the job .yaml, which submits a machine learning job defined in the source job YAML file to the Azure Machine Learning workspace. This demonstrates how GitHub Actions can automate or manually trigger Azure Machine Learning training jobs as part of an MLOps workflow. A simple workflow logs into Azure, then runs the Azure ML job create command to submit a predefined training job to Azure ML. A good use case here is a team stores their model training configuration in that job.yaml file in GitHub, and then when a maintainer triggers the workflow, GitHub Actions automatically authenticates and launches a model training job in Azure ML, all without leaving the repository. Registering a model is the moment your experiment becomes a reusable, production-ready asset. In this section, you'll see how to take a trained MLflow model and register it in Azure Machine Learning, making it discoverable, versioned, and ready for deployment or monitoring. Think of the model registry as your single source of truth for models. Instead of scattered files or scripts, every version of the model, along with its metrics, parameters, and lineage, can be tracked and managed in one place, so teams can confidently deploy, compare, and update models as the solution evolves. Now we see how MLflow logs trained models during the experiment, giving you a clear path from experimentation to deployment. MLflow can store a model in two ways: as an artifact, just a file like model.pkl, or as a registered model, which adds structured metadata and makes the model easier to track, version, and reuse in Azure Machine Learning. When logging a model in the MLflow format, an ML model configuration file is automatically created in the output directory, capturing the environment and metadata needed to reproduce and deploy the model reliably. Consider training a diabetes prediction model. When the run completes, the MLflow logs the trained model and its environment files, so the exact model artifact and dependencies can later be registered and deployed directly to an endpoint or pipeline. The MLflow ML model file is essentially the playbook that tells the world how your model works and how to run it. It captures critical metadata such as where the model artifact is stored, like the artifact path, the exact run and model identifiers with the run ID and the model UUID, and most importantly, the model flavor, which identifies the machine learning framework used to build the model. For example, like our scikit-learn, our TensorFlow, or PyTorch. Equally important is the model signature, which defines the expected inputs and outputs and acts as a strict data contract between the model and any service or application that calls it. To make that contract clear, MLflow supports two signature types. Column-based signatures are used for tabular models that accept a pandas data frame, while tensor-based signatures support an n-dimensional array like numpy.narray, common in image or text models. Consider that if you deploy a churn prediction model, the ML model signature ensures the scoring service receives the correct columns, for example, tenure, balance, and activity. Consider also to always include a well-defined flavor and signature when logging MLflow models. This guarantees the model's dependencies, data scheme, and interface are clearly defined, making deployment and reuse far more reliable. Now it's time for our knowledge check. Question 1. A data scientist trains and logs a model with MLflow. When the data scientist deploys the model, the schema of the model's input and output isn't correct. What should the data scientist customize to fix the issue? Answer: customize the model's signature. Question 2. A data scientist trained a deep learning model with TensorFlow. The deployed model is compute intensive and needs to use the most optimal interface server for similar workloads. Which model type is compatible with compute intensive and no-code deployments? Answer: Triton. You've now seen how MLOps brings structure, reliability, and scale to machine learning beyond the notebook by combining version control, automated training with GitHub Actions, MLflow tracking, model registration, and continuous monitoring. Teams turn one-off experiments into living systems that evolve safely over time. This is where machine learning becomes operational. Models are traceable, deployments are repeatable, and performance is continuously observed as real-world data changes. With these foundations in place, you're no longer just building models. You're running an end-to-end ML lifecycle that can retrain, redeploy, and improve with confidence, delivering AI solutions that remain trustworthy, resilient, and ready for production impact. Thanks for joining us for this session. To continue your learning, watch other videos in this course, or explore more on Microsoft Learn at aka.ms/learn.